Today, companies hire ML engineers who build production-grade AI systems, not just train theoretical models or wipe code. So in this video, I'll break down 4 deep learning projects you can confidently list on your resume to show that you understand real AI systems. I'll also show you exactly what to build, what tools you need, and high-level steps to follow. Now make sure to stick through to project 4. It's where most engineers stop, but finishing it what actually sets you apart in today's job market. So let's dig into it. Hi, I'm Sam. I've spent a decade building tech products. On this channel, I share career advice that you can apply right away. In your project number 1, you'll be creating multimodal embeddings with SIGLib2. Wait. What the hell does that even mean? Say you are an AI ML engineer in the marketing department. Your company spends money testing ads to see which image or caption performs better. The problem is, company finds out which ad works only after it has already spent a ton of money. Now, the company wants to use deep learning to find out which ad will perform better before spending all that money. And that's a reasonable goal to have. Now, before AI can predict, it first needs to visually understand what the ad is actually showing and saying. And that's precisely multimodal embeddings. In other words, to build vector representation of what's in the image. In deep learning, this concept is called representation learning. It's the first step in modern AI engineering. That is, to build representations that all downstream projects can depend on. So what input data do you need for this? You need image caption pairs, where the caption is the text that describes the image. You can get this dataset from Coco Captions, Flickr 30K. Download links are on the screen. Or if you like, you can even curate a small set of marketing visuals with short taglines. The goal here is simple. Turn those images and captions into embeddings, numeric vectors that represent the meaning. A successful embedding space shows semantic clustering, meaning the images of beaches and words like vacation and relaxation appear next to each other, while the unrelated items like car and banana sit far apart. That visual separation is how you know the model is understanding the meaning of the image and not just the color or the texture. Now the next question is, what tools do you need and in what order? Well, tools depend on the tasks. First, to generate joint image text embeddings, use SIGLib2. Number 2, to run the model and extract embeddings, you'll be using PyTorch. Number 3, to load models, you'll use Hugging Face transformers. And finally, to visualize how these embeddings group by meaning, you're going to use FAS or UMAP. Links are on the screen. Key takeaway from project 1 is that once you know how to use embeddings, you understand how deep learning systems see and connect ideas. Next comes the question, can the model tell when an image and its caption actually belong together? And that's the focus of project number 2. By the way, if you got a question or a different take, drop it in the comments. I'm always curious to see what you think. And if this is helping you out, please like and subscribe. It tells me to make more videos like this. In project number 2, you'll be measuring how well an image and its caption actually fit together using Qwen 2.5 VL. Now, why does this matter if you have already created embeddings? Because representing meaning is one thing. Understanding whether two pieces of information actually match is something else entirely. So let's go back to our marketing example. Your AI now understands what's in an image and what a caption says. But what if the caption doesn't match? Imagine a coffee ad that says run faster with every sip. I know it's silly, but the words talk about speed while the image shows a person relaxing at a cafe. Totally opposite from the idea of relaxing. So you see the mismatch? And that's exactly what alignment helps you detect. In deep learning, this concept is called multimodal alignment. Technically, models learn this through contrastive learning, meaning by pulling matching image text pairs closer in vector space and pushing mismatched ones apart from each other. It's how modern AI systems move from recognizing content to reasoning about relationships. In terms of input data, you will use the same image caption pairs from the project number 1, but this time include a few intentionally mismatched pairs, where the caption doesn't describe the image. You can get the clean samples from Coco Captions or Flickr 30K, or even make your own with ad visuals and mismatched taglines. The download links are on the screen. Now, we already know that the goal of this project is to measure alignment. But how would you know that? It's simple. Model should return high scores for matching pairs and low scores for mismatched ones. And when you plot the result, you'll see two clear groups: correct pairs clustered together and wrong ones separated. That's how you know your AI isn't just seeing, it's understanding consistency between vision and language. Alright, so what tools help you measure this alignment? Here is the order you will explore them. First, to measure how well an image and caption align, use Qwen 2.5 EL, a model built for vision language understanding. Next, to generate baseline embeddings for comparison, use SIGLIP2 as before. To run models and compute similarity score, you'll work with PyTorch. It's the core deep learning framework. To visualize how alignment scores separate matched and mismatched pairs, you're going to use matplotlib or Plotly. The key takeaway from deep learning project number 2 is that it teaches AI to evaluate whether two modalities truly match or not. By the way, modality in this case means image and text. Now that your model can tell what fits together, the next logical question is, can it predict what will perform better? And that's the focus of project number 3. But first we need to define, what do we mean by perform better? In this case, ad performance means that the ad that gets more clicks. It's that simple. Now, if deep learning feels overwhelming, I get it. I've been there. That's why I made a free guide to help you choose the right role in AI and prep without wasting time. Grab it from the link below. It's free and it'll save you weeks. Now back to our project. In deep learning theory, this concept is called transfer learning or fine-tuning. Now, do you remember the embeddings you generated before? The goal of this project, in simple terms, is to take those embeddings and train a small model to estimate how likely each ad is to perform well. A good model produces a clear predictive signal, meaning high-performing ads consistently get higher predicted score and low performing ones get low score. Now, as before, you need input data for this project. You already have image caption pair, so just tag each image with a performance label like high, medium, low. The idea isn't to build a massive data set, it's to learn how to map meaning to outcomes. In terms of tools that you need, first, to train a small predictive head efficiently, use PyTorch Lightning, which structures and simplified fine-tuning. Then, to experiment quickly with regressors and classifiers, use scikit-learn for a lightweight start. To track metrics and visualize improvements, use weights and biases to log runs and monitor model performance. The links are on the screen. Now let's take a step back and understand one more time. Project 1 helped your AI see and represent what each ad is showing and saying. Project 2 helped it judge whether the image and message fit together. And this project, that's the project number 3, helps it predict which ad will actually perform better before spending the money. But what if the model could evaluate its own reasoning and explain why it made that prediction? Wouldn't that be great? And that's what you will explore next in project number 4, enabling self-evaluation and feedback using LLaVA-Nex. I'm sure you must be thinking, I should stop now, and why even care about this advanced topic? Here is why. This ability to reflect and reason about its own decision making moves your AI one step closer to real-world intelligence. The core principle here is the self-evaluation and feedback, often implemented through multimodal reasoning. The goal of this project is to make your AI explain its own predictions about ad performance. For example, instead of just saying this ad will perform well, the model should respond with something like the image evokes energy and the caption emphasizes speed, both align with the target emotion. In terms of input data, you will reuse the image caption pairs and prediction results from the previous projects. You already have the content, that is the image and caption, the predicted outcome, that is the engagement score. What you don't have is the context, that is what worked or what failed. Now, based on the actual results or your own observation, you provide that context so the model can learn to analyze why a prediction makes sense or doesn't. In terms of tools, here is the actual order you will explore them. First, to generate self-evaluation and reasoning, you're going to use LLaVA-Nex, a model that can interpret both visuals and text. To run the model, as previously, you're going to use PyTorch and Hugging Face transformers. The key takeaway from project number 4 is that reflection and self-evaluation is the new frontier of AI. It's what makes models not just intelligent, but also trustworthy. But here is the catch. Projects alone are not enough. Without a step-by-step learning roadmap to support these projects, it's easy to miss out on the foundations. And that's what I will show you in the next video. How to take these projects and fit them into a clear learning path that can actually take you from beginner to an AI engineer.